Yeah, so I've got a bunch right now. Assuming that wait, hold on. So, can you already take this one? No. Yeah. And I didn't. I don't right. What about? I want to make a yeah. And I got only to make that a project. First, with the sound. Yeah. Well, we also have so now yeah, well, I mean, we have most of these. Oh, nice. Yeah, so all we have to do is yeah, right now we're just working on the electronic components of our project. And so I'm doing right now, all we do is three different types of abilities. Yes, and because we didn't have back powers. So all we need. And wait, well, you're saying that they don't have that. No. Because we have to get a custom set for our do it. Yes. You need custom weight. So I'm for custom. They all have we have some one for inside. So designing a part. And just like several others. So we had to get just like it's bad. We did yeah, but I don't think we know you have to help to like change the dynamics of the world real. We'll figure it out.
What's up? Yep.
Yeah. Yeah.
Problem, there was a question about system problems. It's a distance.
There was one like that in problem too.
Oh, from here.
Oh, to where it gets turbulent, right?
Yeah.
Yes.
Can I go over here?
A little bit. So we know that like, for external flow, it goes turbulent when the Reynolds number is equal to 5 times temperature, right? The Reynolds number is equal to U infinity times L divided by D, right? So this is the critical Reynolds number, right? And so for these problems, the velocity that I give you, this is usually fixed. And so this is a fixed value. Density is, viscosity is also fixed, right? And so, if you know what the Reynolds number has to be, and then you just use that to solve for
Oh, wow.
Yep.
Okay, thank you.
Yep.
So I guess so what's up your mind?
No, Thursday. Thursday, it's just the fun. Oh, 4:31. We started lecture. I mean, probably not. Unless, honestly, learning about it.
Oh, also, Professor.
Yeah.
So I noticed that when using the calculator,
Yeah.
it gives us slightly different numbers.
Yeah.
And our answers come out slightly different than the ones that are provided.
Yep.
before.
Yeah, that's fine. So there's going to be a lot of variance in these answers because every calculator is going to be a little bit different, and the book values are going to be a little bit different too. And so, yeah, that's fine.
Is there any like preferred, so like?
Not really. I mean, most of the time you're going to be like your first 3 or 4 digits are going to be the same anyway, and so everything else is like very minimal errors. There's no number. I mean, I'm looking at your guys' process, and so if I can see that the process you guys are following is correct, and I can tell just based on the property value that you write down, whether you're on or not. And so, yeah, don't think about it too much. Just
That's what we covered today.
I've been just trying to do no problem. That's what you like.
I guess so, maybe. Some people are online.
Yeah. Yeah, that's the normal.
I mean, it's the first spring break, COVID's probably at the lowest it's been in a while, and so people are probably getting off. These lectures are recorded too, so people can watch them anyway if they want.
I kind of like.
Nice. That's good. Nice.
And then we have to plot both of them. The first one. Some people do just get up, they were done. We just run out of time, so we today's 20. I think you're thinking. I did a 6-4 to solve my things. But what happened was at the very end, I couldn't get my legends to work properly, so I had to do. Wait, did you put it at the very end, or did you put it? I put it at the outside of the 4 loop. Should you be running it in the 4 loops since you're going to be plotting? Because the 4 loop plots it for you, right? I tried inside it breaks it for me. It's not like. It's not hurt. It's not flexible. It's like.
Hey, Kevin.
There's a problem with that. We have like 2 plots. One was like. Second one. Just do it, man. I'll just copy this photo, I'll say,
All right, it's 2:30, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today? Last week before spring break, and so it's exciting, but also makes this week very difficult to get through. So we have 2 more lectures, and then you don't have to see me for a week, and then we'll come back after spring break for the final sprint towards the end. Okay, and so plan for today is we're going to continue our lecture notes on internal force convection. So we started a little bit of it at the end of class last Wednesday, and so we're going to continue on today. Homework 4 is due this Friday, and so remember, make sure that you're doing it. Okay. I'm not going to. I do have your next homework assignment. I am working on it, but I'm not going to assign it until after spring break. So I know you guys have been working hard, getting the homeworks done in the midterm. So I want you guys to take a break from this class during spring break, and then we'll come back and I'll work you harder after spring break. No, I'm kidding. It'll be the normal amount. Okay, and so I think that's it for my announcements. Are there any questions I can answer before we get started? Okay, all right, so let's go ahead and continue. All right, we were talking about internal convection. All right. And so just to kind of refresh your memory, when I say internal convection, these are convection heat transfer situations when your flow is bounded, okay? And what I mean by bounded is that the flow is going to be basically engulfed or surrounded on all sides. Okay, because before, when we were doing external convection, and I'm sure everyone's, you guys have been working on this for homework 4, right? We had just a single surface right here, and so when we had flow that was coming in, right, we know that when fluid flows past a surface like this, then a boundary layer is going to form, right? Okay. And for external convection, that boundary layer can kind of just grow as much as it needs to. Okay, so it can get as big as it wants. But for internal convection, we're going to add a surface on the other side. Okay, so now the flow is completely surrounded. And on the other surface, we're going to have a boundary layer that forms as well. Okay, let me clean this up a little bit. Okay, and so because we have a boundary layer forming from the other surface, eventually those two boundary layers are going to merge together. Okay, it's going to be and so what happens after that, in this region, which we call the fully developed region, okay, in the fully developed region, we're going to have very different fluid dynamics than we do in the free stream. Okay. And so the situation here is going to change quite a bit, because instead of having the boundary layer as being kind of this small thing, that we don't really, in the last weeks, we kind of talked about the boundary layer, but it didn't really make that much of an impact on our calculations. Here it's going to make a big impact, because we're basically going to be entirely boundary layer. Okay. And since convection heat transfer is so closely related to the fluid mechanics, right? If the fluid dynamics are going to change, then it's going to change our entire situation. Okay. Right? And we're not going to talk about it too much, but this region of the flow where the boundary layers have yet to merge, this is what's known as the entrance region. Okay. But that's just a little trivia. We're not going to focus too much on it. Mostly just because both the fluid mechanics and the heat transfer in the entrance region are pretty complex, but it is good to know just what it means. Okay. All right, so what does this mean quantitatively for our analysis, right? So usually when we compute heat transfer for convection, we use Newton's law of cooling, right? That's the formula that we use. And so when we want to compute convection heat transfer, okay, we take the convection coefficient multiplied by the surface area, and we multiply by the difference between the surface temperature and the free stream temperature. Okay, that's what we usually do. Except now, because we're in the fully developed region, we're going to lose all concept of what this is. Okay. Because if you're looking at the free stream temperature out here, right, of course, you know what the free stream temperature is out there. But once the boundary layers merge, we don't know what the free stream temperature was kind of before we got to this point. Okay. And so we need to modify this equation a little bit. Okay. Right, mathematically, it's going to be exactly the same. It's just, the way you interpret it is going to be a little bit different. Okay. And so for internal convection, we're going to have Q convection would be equal to H. Okay. We're still going to be computing H. Okay. And so remember, that's a big focus of this unit, is how to compute H. Okay. We're still going to have a surface temperature. And so that's still going to be important. Okay. But instead of T infinity, we now have Tm, where this Tm here stands for the mean temperature. And whenever you say mean, that means you're taking the average of something. And so it's important to clarify that this is the mean temperature across the cross section. Okay. Right. So we're going to be working with the bottom equation here. Okay. Mathematically, it doesn't really make that big a difference. The formula, you can argue the formulas are exactly the same. But again, it's how you interpret, how you envision T infinity and Tm. Okay, and we're going to spend a bit of time today talking about the differences in between them, and why I'm kind of making such a big deal of this distinction. Okay. All right, and so I think that's about how much we covered last Wednesday. So are there any questions on any of this so far? Okay. All right, so let's talk about turbulence for a second, okay? Because that's going to change as well. Remember, the way that we compute, or the way that we determine whether a flow is turbulent, we have to compute the Reynolds number, right? Okay. So our definition of the Reynolds number is we have some velocity multiplied by a length, okay? In this case, we're going to assume that we have, we're going to concern ourselves mostly with pipe flow. And so the length scale that we're going to use is going to be the diameter of the pipe, okay? And of course, then we have to divide by the viscosity. Right. But just like the change that we made for the, for the convection heat transfer, we're going to make a similar change here as well, okay? Because we're not going to have U infinity anymore, because we don't know what U infinity is at all, okay? Because we're in the fully developed region. And so what we're going to do instead is we're going to use the mean temperature, or the mean velocity, excuse me. And so again, that UM stands for the mean velocity across a cross section. Okay. And we'll talk about ways about how we can compute that as well. All right. And another difference that we're going to make compared to external convection is that for external convection, remember the critical Reynolds number, which is the Reynolds number that you have to reach in order to have turbulent flow, right? This was 5 times 10 to the 5th for external flow, right? For internal flow, we have a much lower threshold. Okay, so it's not that for internal flow. Okay, and so for internal flow, our threshold is actually 2,300. And so if your Reynolds number, the way that you compute it up there, if it exceeds 2,300, which is very small, it is a lot smaller than 5 times 10 to the 5th, then you're going to have turbulent flow. Okay? And part of the reason why it's so much lower is because of that boundary layer merging thing that we talked about, a bit earlier. Okay? Because in situations where the boundary layers converge, you get much more chaotic flow at much lower velocities. Okay? So it's a lot harder to keep the flow kind of tame and orderly, when you have kind of bounded walls in between. Okay, any questions on this so far? Okay. Okay, so let's start talking about the thermal side. Okay. All right, question. So is there a large error taking UM as the average rather than as a function of X and Y? Yeah, that's a good question. And so, so what Keith is referring to is the fact that, when you have pipe flow, actually, let me just draw it here and I'll just erase it. Okay? And so when you have pipe flow, you have velocities that kind of vary at every coordinate X and Y, right? And so the most common form for pipe flow velocity is some kind of parabolic flow. And so when I say, mean velocity, UM right here, what I'm saying is that, we're going to take the average of all of these velocities here. Usually it's somewhere like around here, okay? That's UM. And so the question is, is there any error associated with taking the mean of this as opposed to, taking its spatial variation into account? And of course, anytime you take an average, there is going to be some approximation. But because Reynolds number is kind of defined as kind of like an overall quantity, most of the time you're going to use a mean value there. And it's the assumption that you're going to use a mean, especially when you're talking about turbulence too. So turbulence is kind of a description of how the flow kind of behaves overall. And so with that in mind, it kind of makes the most sense to use a mean value for that. Because if you use, I've seen what other people have done is that they use kind of the maximum velocity to compute Reynolds number. And that has its uses. But for determining whether the flow is kind of overall turbulent or overall laminar, it kind of makes more sense to use the mean there. And so there is, to kind of answer your question, quickly, there is some error, but just the way that we define our terms here, it kind of minimizes that as much as possible. Yeah. Okay. Thermal boundary layers. All right, and so for the thermal considerations, we have kind of the same thing. Okay, let me go ahead and draw our pipe again. Okay. And so just like in the fluid mechanics case, we have our free stream temperature coming in. Okay, but very quickly we lose all sense of that because eventually, our two boundary layers are going to merge. Okay, and instead, we have a mean temperature here, which is the average temperature across this entire cross section. Okay. And so if I assume that this is like a cylindrical pipe, the Tm is kind of the average temperature across that section. Okay. Okay. So this right here is the entrance length. All right. And so the first thing you can do is you can actually compute, how an approximation for how long your entrance length is. Okay. And so the formula for that is we have X EL. Okay. And so that's the length of the entrance region. And we divide that by the diameter. Okay. Experiments have shown is that this quantity here is equal to 0.05 multiplied by the Reynolds number, based on the diameter, and so based on the the formula that we have up there, okay, multiplied by the Prandtl number. And so this is a formula that can tell you, how long your entrance length is. For most cases, if you end up plugging everything into this formula, you'll find that it's extremely small. And so if you have a pipe, usually you could compare the size of a pipe if you compare the diameter to the length. Most pipes have a much longer length than they do diameter. And so what you'll see is that the entrance length is also going to be very, very small here as well. Okay. And so you can compute this, I'm not going to dwell too much on it, but if you compute this for most of the problems that we have, you'll see that this is only a fraction of the length. And so, for most cases, we're just going to ignore the entrance length. And this is kind of the justification for this. Okay. Okay. Any questions on this so far? Okay. And so let's talk about TM. Okay. So in other words, let's find out how we can compute that. Right? But before we can compute that, we have to kind of understand a bit more about how it's different than the mean temperature or the free stream temperature, excuse me. Okay. And the biggest difference, in between the two is that if you compare the free stream temperature and compared to how we used it in the previous chapter, okay, the mean temperature here is actually going to change. Okay. So it's not going to be a constant. Okay. And so this is a really big difference because when we did external convection, right? So we did Q is equal to HA TS minus T infinity. Okay. We had always assumed that the T infinity was a constant, right? And so we never really questioned it. And so we said, that's just the temperature of the air. the temperature of the air is the temperature of the air, and no matter what we did to it, T infinity never changed. Okay. This is a big difference now because Tm is actually going to change. Okay. And why is that? Okay. And so this is because when you have internal convection, what you have is kind of a finite, you could think of it as like a finite amount of space, or the amount of space that where the fluid occupies is much smaller. Okay. If you think about our external convection cases, right? So you think about, flow, I'll take the homework problem, for example, right? So you think of flow over a big rig truck that's driving on the freeway, right? And when we think about the temperature of the air, the air is massive, right? And so if you look at the air on top of a truck on the freeway, right, there's just so much air, right? And so one little truck that's driving on that freeway, no matter if the truck is carrying, liquid nitrogen, it's not going to make that much of an impact on the air surrounding just because there's just so much of it, right? Same thing as, let's like take the ocean, for example, right? The ocean is kind of another good example. If you took a piss in the ocean, right? So your piss is usually a lot warmer than the ocean, but it's not really going to change the temperature of the ocean because there's so much ocean and you're only one man, so you only have so much piss, right? So in external convection, we assume that our free stream conditions were kind of like I almost think of them like a reservoir, like an abyss, right? For internal convection, we don't have that, right? And so the amount of fluid that we have is just whatever is between these walls, okay? And so whenever we do have some kind of heat transfer that goes into or out of the fluid, that's actually going to change the thermal state of the fluid on the inside. Don't piss into the ocean, by the way. Doesn't matter if you're on a boat and there's no laws, people will still look at you weird. Not speaking from experience, by the way. Okay. And so, if we have this case right here, so let's say that we have the usual case where our surface here is hotter than our fluid, right? And so heat is coming into the fluid, right? And that's happening all throughout the pipe. And so if heat is coming in, and we measure the mean temperature at this location, right? So we'll call this TM1. And we measure at a different location, TM2, right? Because heat is coming into this finite amount of space, TM2 has to be greater than TM1 because it's just gaining heat. Okay? And so that's kind of the big difference between, how we're going to treat internal convection situations and external ones. Okay. All right. Any questions on this? Okay. All right. And so, unfortunately, that does kind of complicate our analysis a bit because, we can't treat that T infinity or Tm as a constant anymore. Okay. But luckily for us, even though the value of Tm is actually changing, the shape of the temperature of profile does not actually change with X. Okay. And so even though that mean temperature itself is going to be changing, the mathematical term for this is that all the temperature profiles along the length, they're all self-similar. And so they all even though they're all different shapes, they all kind of have the same shape. Okay? Think of them as like, parabolas, right? So they're all, you can raise or lower the parabola as much as you want, but there's still going to be parabolas at the end of the day. Okay. All right. So mathematically, the way that we can express this is that we take the derivative, okay, with respect to z, where z is the dimension down the length of the tube. Okay. And we take the derivative of Ts minus T of R, okay, where T of R is the spatial distribution of temperature within the pipe. And we divide that by Ts minus Tm, where Tm is the mean temperature. This is 0. Okay. Okay. So this is actually a pretty nice result, because even though we do have a very different situation, this is actually going to simplify things a lot for us. And so the consequence of this, and I'm not going to go too much into the mathematical details or the physical details, but you can find a lot of them in the book. Okay. But the consequence of the fact that even though our temperature profile is not going to be changing, okay, our mean temperature is changing, but the shape is not changing. So the result of this is that if you take the derivative of the convection coefficient h with respect to z, okay, this is also going to be 0. Okay. Okay. And so what this tells us is that, even though the mean temperature is changing, the convection coefficient that actually, that we actually use to compute temperature, or excuse me, to compute heat transfer, that is not changing along the length of the tube as well. Okay. And if it's not changing, the opposite of not changing is staying constant. Okay. And so our convection coefficient here is going to be a constant. Okay. And the result of this is that if our convection coefficient is constant, then our Nusselt number is also going to be constant, right? Remember, our Nusselt number is defined as our convection coefficient multiplied by the diameter divided by Kf. Okay. And so if our convection coefficient is not changing, that means this is also not changing. And so all of this is equal to a constant. Okay. And so we might not get to it today, but on Wednesday we'll actually, I'll actually give you the convection, or excuse me, the Nusselt correlation for internal flow. And I guarantee you everyone will be upset with me, because we're going to do all this work, all this derivation, go through all these examples, and then you're going to end up with Nusselt number. I forget exactly what it is. It's like Nusselt number is equal to 4 or something like that. Right? It's not even a formula. It's just Nusselt number is equal to 4. And so, I'll let you know now so that you won't be upset at me later. But that's all. That kind of always happens at this stage of the class. Okay? And so kind of our focus is going to shift a little bit in this section, right? And so in the previous section, right, we focused all of our attention on finding H, right? H was kind of the difficult part. In internal convection, finding H is actually not going to be it's not going to be as hard as before, okay? What is going to be hard instead is finding this mean temperature. Okay? And so we're going to focus most of our efforts on finding what that mean temperature is under different situations. All right. Any questions on any of this? Okay. All right. So let's go ahead and talk about how we can actually find that mean temperature. Okay. And so let me start this derivation by drawing out our pipe again, okay? And then let me draw kind of a very small control volume. And so I'm just going to take a very small parcel of fluid, okay? Because I'm going to surround it by dotted lines. And so headed this way, we're having fluid that's flowing through. Okay? The fluid that's flowing through has a mass flow rate of m dot. Okay? So this symbol here is mass flow rate. And if you recall, mass flow rate has the units of kilograms per second. Okay? Those are its SI units. The relevant length that we're going to talk about. So the length of this parcel will be dz. Okay? And so we put a d in front just to remind you that this is really, really small. Okay? And because of convection, we're going to have a convection heat transfer, and we're going to assume that's going into the fluid. Okay? But because our parcel of fluid is so small, we're going to have a very small amount of heat transfer. Okay, so we'll call that dq convection. Okay. So let me just write off to the side. Consider a very small parcel of fluid. Okay. And so what we're going to do is that, based on these situations, we're going to, formulate some formulas for Q convection, okay, based on what we know already. Okay. And so one expression that we have for dq convection, okay, is we're just going to use our Newton's law of cooling, right? So one that we already know. So we say that dq convection is equal to H times the surface area multiplied by, H times dA, because it's a very small area. Okay. And this is going to be multiplied by Ts minus Tm, right? Where dA here, this is the surface area of our tiny parcel. Okay. It would be great if we can put this in front of in terms of dz. Okay. And so what we can do is we can say dA, which is the internal surface area of a cylinder. Okay. This is going to be equal to the perimeter of the pipe. Okay. Multiplied by dz, right? Okay. So I'm going to assume that this is not, we're going to be a little bit more general here. So, we're not going to assume that this is a cylindrical pipe. Otherwise, you can plug in perimeters equal to pi times the diameter, but we're just going to leave it general for now. Okay. And so that's one expression that we have for dq convection. So we have dq convection is equal to H times P times Ts minus Tm times dz. Okay. So all I did to get that was just, apply our Newton's law of cooling to this tiny parcel of fluid. So that's one expression for dq convection. Okay. Another expression that we can get is by applying just conservation of energy. Okay. And so by conservation of energy, and knowing the fact that this is a finite amount of fluid, we know that if we apply heat, or we apply any kind of, we insert kind of any kind of thermal energy into, something that's finite, it's going to cause a change in temperature, right? And so the way we can express that mathematically is that dq convection, right? So this is the amount of heat that we're putting in. Okay. And then on the other side, we have dTm. dTm will be the change in thermal energy for this parcel. Okay. So this is like coming back to our transient heat conduction days, right? So remember when we talked about transient heat conduction, any heat that goes into or out of a material is going to change its internal energy. Okay. But of course, these two quantities, their units don't match. And so we need to add some quantities here in order to make them match. One quantity that we're going to add is the mass flow rate m dot. And then we're going to multiply by Cp, where Cp here is the thermal capacity. And so this expression down here is kind of more, it's very similar to how we thought about heat transfer from transient conduction, okay? Right, so any heat that you put in, it's going to change, it's going to cause a change in, in internal energy. Okay, and so hopefully you kind of see where this is going. And so, in both expressions here, they both are equal to dq convection. And so again, by conservation of energy, these two quantities have to be equal to each other. Okay. Okay. And so on the one side, we have the contribution from Newton's law of cooling. So we have H times P times Ts minus Tm multiplied by dz. Okay. This is equal to m dot Cp times dTm. Okay. All right. And so what I want to do, I'm going to manipulate this expression a little bit. And so on the, I'm going to take this entire expression and I'm going to divide it by dz. Okay. And so that's going to eliminate dz on the other side. And I'm also going to divide it by m dot Cp. So that takes m dot Cp and from the right and moves it over to the left. Okay. All right. And so if we do that, on the one side of the equation, we have H times P divided by m dot Cp. Okay. We multiply that by Ts minus Tm. And on the right-hand side, we have dTm dz. Okay. Which by, some might consider mathematical sacrilege, but we've ended up with a derivative, right? And so we didn't start with derivatives, but by dividing two things, we ended up with one. So, so that's great. Okay, and so this expression right here is a way that we can express how the mean temperature changes along the length of the pipe. Okay. Okay. And so next we're going to work on this equation here and solve it under a couple conditions. Okay. Because we can't quite solve it yet because it is, we'll talk about that in a bit. And so we're going to impose a couple more assumptions before we can actually solve this. But any questions on this before we we use those assumptions. Okay. All right. And so, normally, you would look at an expression like this and you would say, let's just integrate this guy. And so, let's use to separation of variables or something, and let's just integrate. Okay. The problem with that is that if you look at the expression for Tm being the mean temperature of the fluid, and TS, okay, we didn't really talk about TS just yet, but TS kind of follows the same rules. Both of these are going to vary along the length of the pipe. Okay. And so in a sense, we kind of have one equation, but two unknowns. Okay. And so we can't really solve for this expression just yet. At least not in the general sense. But what we can do is we can apply some assumptions in order to make this thing solvable. It ain't that scary. Come on. Okay. And so let's apply one of these assumptions. And so the first assumption that we're going to make is we're going to assume that the heat flux from the wall is constant. It's funny when that went off, my high school friend was actually calling me just now. I keep telling him not to call me in class, but he does it anyway. Okay. That's what I thought at first too. Because I've had that happen. I've had my friends take my phone and change their ringtone whenever they call, or change the image. One of my friends from college, whenever he would call me, and I haven't changed this because I find it hilarious. I have a big image that says the chosen one whenever he calls me. Okay, and so for constant heat flux, that means that this quantity right here, right, which comes from our, Newton's law of cooling, right? So the only thing that's missing here is just the area. But when heat flux is constant, that means this whole quantity is a constant. Okay, maybe Ts itself will change, Tm will change, but their difference is always going to be the same. Okay, and so we take that in mind, and so if we come back up to this expression right here, and I kind of rearrange the terms a little bit, so we have P divided by m dot Cp multiplied by H times Ts minus Tm. Okay. We know that this quantity right here, this is just going to be a constant. Right? Right? And that's great because what else do we know about perimeter, right? And so we're going to assume that our pipe is not going to change cross-sectional area, right? And so we're going to have just a straight pipe. And so for a straight pipe, the perimeter also going to be constant. Excuse me, this should be dz, not dx. Okay. Mass flow rate, and so that's the amount of mass or the rate at which mass is transferring down the length of the pipe. Okay. If you remember from fluid mechanics, if you have just a single pipe, if you measure the mass flow rate at one location and another one, it should be exactly the same because you have to conserve mass down the pipe. Okay. And so this is also going to be constant. Cp here is the thermal capacity, and that's just a property of the fluid. And so this is also going to be constant. Okay. And so would you look at that? Everyone in this expression is a constant. And so no one wants to change, which is great. Okay. And so when everything on this side is a constant, it's like this whole thing is just a number. So you can assume that, just for the sake of argument, everything multiplied together here is something like 5 or something. Right? And so if everything over here is constant, we can just straight up integrate this entire expression. Okay. So remember, what we want is Tm, right? And so everything on one side of the equation is constant, we can just integrate, okay, with respect to z. And that's going to, form our expression. Right? And so if we do that, on one side of the equation, we have Tm as a function of z, okay? And on the other side, we have P H divided by m dot Cp times Ts minus Tm. Since that entire thing is a constant, when we integrate a constant, we just get the constant multiplied by our integration variable. Okay, so we have pH divided by m dot Cp, Ts minus Tm multiplied by z. Okay. But because we're doing a indefinite integral, we have to add our arbitrary constant. Okay. But since this is a simple case, I kind of just plugged in the constant for you. Okay. And so what this constant is going to be the mean temperature at the inlet of the pipe, or wherever we define z is equal to 0. Right. So this is the mean temperature distribution when heat flux is constant. Okay. And so if we graph this, right, I love graphs because they it's much nicer, I think, to look at a graph than to look at a function, right? In this case, there's a lot of terms here, but the only z dependence here is just purely linear. Okay, and so our graph should just be a simple linear graph. Tm, and then by extension, because the heat flux is constant, that means Ts must also go up at the same rate. Okay, because the difference in between these two has to be constant. And so in the case of constant heat flux, you have the mean temperature that just goes up linearly down the length of the pipe. All right. Any questions on this before we do an example? Okay. All right. So let's do an example to see how it all comes to play. Because we've been doing kind of a lot of derivations in theory today, but let's see it kind of in action. Okay. And so let's look at an example. Let's look at a water heater. Okay. And so let's say we have a water heater and it's responsible for heating water from 20 degrees Celsius to 60 degrees Celsius. Okay. Okay. And the way it accomplishes this is that it basically supplies a constant heat flux through a pipe. Okay. So let me go ahead and draw the situation for you. And so we have a pipe. Okay. So we're looking at the cross section of the pipe. And so when we say that the water has to be heated from 20 degrees C to 60 degrees C, that means if we take the mean temperature at the inlet here, this is going to be 20 degrees C. Okay. We're assuming that the flow is moving this way. Okay. And if we measure the mean temperature at the outlet, This is going to be 60 degrees C over here. Okay. All right, so the flow is moving from left to right, and it's heating up by 40 degrees C. All right. And so we're also given the mass flow rate, and so the mass flow rate here is going to be 0.1 kilograms per second. Okay. And we also know the temperature, the surface temperature at the outlet, so TSO. So the surface temperature at the outlet is going to be 70 degrees C. Okay. And the other thing that we know is we actually know the amount of heat flux that's coming in. Okay. And so the amount of heating that the water heater is providing, so we'll call that QS double prime, is going to be 1.5 times 10 to the 4 watts per meter square. Okay. And so here you kind of see a good illustration of a lot of the concept that we've been talking about, right? And so we have an internal flow situation because, you know, we have flow in a pipe basically, okay? And because the amount of water inside the pipe is finite, when we apply this heating, when we apply this 1.5 times 10 to the 4 watts per meter square, you know, it's going to heat up the water, right? Because there's only a finite amount of water. It's different than our external convection. Okay. We also know the diameter. Yep.
So if the water was finite, it wouldn't even heat it up.
Exactly. Yeah. So it'd be like, you know, trying to heat up the ocean from your boat, right? Yeah. But because, you know, we have kind of a small pipe here, then we can heat the water. All right. So the diameter of the pipe we'll say is 20 millimeters. So it's a fairly small pipe. So it's only 2 centimeters in diameter. Okay. Okay. So based on this information, let's go ahead and compute. Okay. First thing we want to compute is what is the length of the tube required to meet these conditions. Okay. Because we have the heat flux, we have the, you know, the inlet outlet temperatures, but there has to be a certain length of tube that actually, you know, accomplishes this situation. Okay. And the other thing that we can compute, since we're given the surface temperature at the outlet, excuse me, so this should be TSO. Okay. And so based on the surface temperature of the outlet, and based on, you know, the other quantities in the problem, you know, we can actually compute the convection coefficient. All right, any questions on the setup of the problem before we start solving it? Okay. All right, so let's go ahead and start solving it. So this will be part 1. Okay, and so since we know this is a constant heat flux situation, then we know the expression for Tm of Z. Okay? Oh, and if in case it wasn't clear, you know, when I say Z direction, I mean this direction right here. And so the Z direction is just down the length of the tube. And so let's go ahead and use our expression for TMZ for constant heat flux. All right, and so we have, and so I'm just gonna write down the formula that I have up there. Okay? So Tm of Z is equal to P divided by m dot Cp. Okay, times H Ts minus Tm times Z plus Tm of 0. Okay. Okay. So let's go ahead and start plugging things into this expression. Right? Right. So let's start with this. And so this is H times Ts minus Tm. Right. Remember, we're saying that this quantity is constant because this is the constant heat flux. Okay. And so this quantity right here will be QS double prime. And that was given to us straight in the problem, so we can just pop that right in. We're also given m dot in this problem. And so m dot we know is 0.1 kilograms per second, right? Just given to us straight from the problem. We can also compute the perimeter. Okay. So remember the perimeter, in this case, we have a cylindrical pipe, circular cross section. And so perimeter is just going to be the diameter of the pipe multiplied by pi. Okay. And then lastly, we have CP. Okay. And so CP here is the thermal capacity for water. Okay. And so since this is a physical property of our fluid, we can just look this up in a table, or you can use an online calculator, whatever you want. Okay. But we're at a little bit of a dilemma here because, remember these physical properties of water or any fluid, they depend on the temperature, right? And once again, we have a situation where our temperature is not exactly constant throughout this entire thing. Okay. And so what we can do here is very similar to what we did in the external convection, is we just kind of take an average temperature of this entire system. Okay. And so we can use the fact that, we're already given the mean temperature across this cross section. Okay. And so the average temperature across, on this entire segment of pipe is going to be the average between these two. Okay. Exactly. Yeah. And so this is going to be, the difference, or kind of you add up the TMI and the TMO, you divide by 2. And so this is going to be 80 divided by 2, which is 40 degrees C. Okay. And so in the lecture notes, I looked this up in one of the tables in the book. But again, you can just use an online calculator for this. And so what you get from that is CP is equal to 4179 joules per kilogram Kelvin. Okay. Okay. And so let's go ahead and plug in all those numbers. Okay. And so we plug in all those numbers, we have Tm of Z is equal to 2.255 times Z plus Tm at O. Okay. Yep.
What table should we use for?
Here I have table 8.6. And so that's going to be in the appendix, the 6th one. So I think that's properties of water. Yeah. Okay. And so we're just about done here. And so, the only thing we have to plug in for now is Tm of Z and TMO. Okay. Even though it goes by a different name here, we know that TMO is just going to be, or Tm of 0, excuse me, Tm0 is just going to be the mean temperature at the inlet. Okay. So this can be Tm I. Okay. And this Tm of Z, this is going to be Tm at the outlet. So this is TMO. Okay. And so we know Tm at the outlet is going to be 60 degrees C. Okay. We know the Tm at the inlet is going to be 20 degrees C. Okay. And the quantity that we're looking for here is actually going to be Z. So we have 2.255 multiplied by Z. Okay. And so if you solve this expression for Z, so you subtract 20 from both sides divided by 2.255, what you get is Z is equal to 17.74 meters. Okay. And so that means that this, this pipe has to be almost 18 meters long. I don't know why my voice is breaking so much today. This pipe has to be almost 18 meters long in order for us to achieve this, these conditions. Okay. And it makes sense, even for a small pipe, 40 degrees Celsius is a big jump in temperature. And so, you have to, either dump a ton of energy into the pipe, or you have to have it be a long length in order for you to achieve that difference in temperature. Okay. And so 18 meters, it might seem like it's really long, but we're also making a big change in the water temperature as well. All right, any questions on this? Okay, and so the other part of this problem is we want to find the convection coefficient. And the hint in the problem was to use the surface temperature at the outlet. Okay. And so if we use our, the fact that we know Q double prime already, okay, from Newton's law of cooling, we know this is equal to H times Ts minus Tm. Okay. And because we're in a constant heat flux situation, this expression is valid everywhere in the pipe. Okay. And so let's apply these at the outlet. And so we have Qs double prime is equal to H times Ts, comma O minus Tm, comma O. Okay. We divide both sides by that difference and we get H is equal to Qs double prime divided by Ts, comma O minus Tm, comma O. Okay. We know all those quantities from the problem. So we know Ts, comma O is 70 degrees C. And we know Tm, comma O is 60 degrees C. Okay. We know Qs double prime from the problem. And so we can just plug everything in and we get an H of 1500 watts per meter squared Kelvin. Right. So we didn't even need our mean temperature equation, because the surface temperature was given to us. All right, any questions on this example here? Okay. All right, so that's the case for constant surface, constant heat flux. Okay. Now let's look at the other assumption that we can make, which is constant surface temperature. Okay. All right, so let's go ahead and bring back our DTM formula. Okay. So we have DTM dz is equal to P times H divided by m dot Cp times Ts minus Tm. Okay. All right. And so previously what we said was the whole quantity H times Ts minus Tm, that was constant, right? But in this case, what we're going to say instead is that only this quantity is constant. And so we're going to end up with a slightly more complicated expression, but it's something that we can solve because now we only have one unknown, which is Tm. Okay. All right, and so to help us solve this, just so that we're not solving an inhomogeneous equation, let's bring back our favorite friend, our excess temperature theta, okay? And we'll set this equal to Tm minus Ts. Okay. And since Ts is constant, we can take d theta dz, okay? And this is going to be equal to Tm dTm dz. Okay, so let's go ahead and make those substitutions. And so we have d theta dz is equal to minus pH over m dot Cp times theta. So notice I have the minus sign here because the way I defined theta was Tm minus Ts. Okay. But what we have in the expression is Ts minus Tm. And so that kind of brings out an extra negative out in front right there. Okay. And so don't forget that negative. That negative is important. Otherwise, you're going to get infinity temperature, which is not valid. Okay. All right, and so now we have this expression here, and so we have d theta dz is equal to this guy, and so this looks familiar, and so we've solved this equation a few times in this class already, okay. And so we can solve this by separation of variables. Okay. And so if we have d theta over theta. So I'm going to bring theta down there. Okay, is equal to minus pH divided by m dot Cp. Okay. Now that the variables are separated, we can go ahead and integrate. Okay. And so on the left-hand side, we have a natural logarithm of theta is equal to minus pH divided by m dot Cp dz or times z. And so, hopefully you guys know the drill at this point. And so, plus c, there's a constant there. Okay. And so we're going to raise this entire expression to an exponent, and then we're going to use that to solve for theta. Okay. But I'm going to take it one step further. And so, because, theta is a nice tool. It does help us out quite a bit. But we're not actually interested in the theta, right? What we're interested in is Tm. And so once we get that expression for theta, then I'm going to plug Tm back into the expression. Okay. Okay. And so if we do that, we get the following, formula. Okay. And so we get Tm of z, which is what we want, right? So this is going to be equal to Tm at 0 minus Ts times exponent. And so that's e to the minus pH divided by m dot Cp times z plus Ts. All right. And so a little bit more complicated of an expression here, but this is familiar, right? And so this is actually very similar to our fin equation that we've seen before. Okay. And so what we have is kind of an exponential decay of the temperature difference between the surface and the fluid. Okay. And so this right here is our temperature distribution. When surface temperature is constant. Okay. So let me go ahead and plot it. And so this can take either two forms. And so if we have a situation where our surface temperature is hotter than our mean temperature, okay. And so this dotted line here will be Ts, okay. Then Tm will kind of raise up and kind of asymptote near it. Okay. Right, so that's what it looks like if the surface temperature is hotter than the fluid. If the surface temperature is cooler than the fluid, we have a situation like this. Right. And so in both cases, what you see here is that the difference between Tm and Ts is exponentially decaying. Okay. Any questions on this? Yep.
Is the vertical axis?
Yes, it is. Thank you. Mhm. Question?
Within the coefficient for the exponent
Do you mean this guy right here?
of the non.
Yeah. So I kind of skipped a few steps. So that was when we applied, excuse me. So when we applied an exponent to this entire expression, And so this C here basically became this. Yeah, so that's after we applied that and we applied our initial conditions. Right. Okay. And so those are our two cases. And so, when you're doing internal convection, you have to ask yourself, am I in a situation where the heat flux is constant, or am I in a situation where the surface temperature is constant? Okay. Because depending on which one that you can assume, it's going to change your expression for T of Z, pretty drastically, right? And so, we have two very different functions here. So we have one that's a linear function, one that is a exponential decaying function. Unfortunately, for most real life cases, you can't really fully assume one or the other. Okay. Okay. And so it's very rare that you're going to get a situation where, yes, you can say the surface temperature is going to be constant throughout the entire pipe, or yes, the heat flux is going to be constant here throughout the entire pipe. Okay. It just doesn't really work like that. And so in real life situations, that doesn't mean that both of these expressions here are useless. Okay. What it means is that whenever you're given a real life situation, you kind of have to make the judgment calls that, is it more appropriate for me to assume that the surface temperature is constant here? Or is it more appropriate for me to assume that the heat flux is constant? Okay. And so that's a judgment call that you kind of have to make. Okay. And of course, that's a difficult thing to do, when you're kind of just learning heat transfers for the first time. But I'll give you a couple examples. Okay, so one example that I think is fairly common is if you have a fairly short pipe. Okay. Okay. And so you don't have very much piping at all. So you have, a pipe that looks like this. Okay. Right. And so the length here, may be only 2 or 3 times the diameter, or maybe even less. Okay. Okay. In these situations, you don't really have that much space here, right? And so, because the distance is so short, the temperatures are not really going to change all that much. Right. And so in a situation like this, you can argue that, because the length is so short, then the pipe itself, the pipe temperature might not change all that much. Okay. Okay. And so TS here, we can assume it's constant just by the fact that, we just don't have that much piping to begin with. Okay. And so this could be a situation where, your TS is constant, and so you assume kind of the second situation as opposed to the first. Okay. Another situation where you can assume TS is constant, okay. And this is fairly common, is if your pipe is made of a material with a high thermal capacity. Okay. Remember when we talked about in transient heat conduction, kind of the idea of thermal capacity, right? And so that's a function of of Cp which is, kind of the amount of energy that they can store, but it's also a function of density as well. It's also a function of just how thick your pipe is as well, okay? And remember, when I talk about pipe material, I'm not talking about the fluid, I'm talking about the actual pipe, the solid part of the pipe itself, okay? And so what you'll see, commonly in practice is you'll see pipes that are made of something like cast iron, right? And so cast iron is this really robust, kind of bulky material. And so cast iron can really withstand a lot of heat, okay? And so in these situations, because the pipe can store that much heat, right? It's usually reasonable to assume that the pipe is kind of relatively thermally static, okay? And so this is another situation where your surface temperature can be constant. Okay, so those are two situations where you can assume the surface temperature is constant. But what about heat flux? Right? And so for heat flux, a common situation that you'll see, and we'll go over this, and we'll go over these in very much more detail after the spring break, is a device called a heat exchanger. And so a heat exchanger is basically a device that's designed to exchange heat between two flowing fluids. Okay? Okay. And so the device kind of looks something like this. And so, you'll have one pipe that's where fluid is flowing, right? You might have another pipe here where fluid is flowing here. Okay. And they're separated by kind of a thin, usually a fairly thin wall right here. Okay. And these devices are usually fairly long as well. Okay. And so in these situations, because these devices are designed to have kind of a constant amount of heat exchange in between these two fluids. Okay. Right. Because of the design of the device, you can assume that the heat flux is going to be constant. Okay. And you'll see after the spring break that this is an assumption that we will actually make for these kinds of devices. Okay. And so again, you're never going to run into a situation where one is clear over the other one, and so you're going to have to make some assumptions to kind of justify them based on the situation. Any final questions before we wrap it up for today? It's because we have such a small amount of space, and so the amount of heat transfer there is going to be small, and so there's not going to be there's not going to be that much chance for the pipe to change temperature. All right, one more question. Okay, so question on the homework. So question on the homework I'll address after. And so thank you everyone for coming today. Hope you guys have a good rest of your afternoon, and I'll see you on Wednesday. Okay. Okay. So problem 4. Oh yes. Yeah. So I got on this question a lot actually. So XC here is you can think of it as the location where the flow first starts to go turbulent. And so the way to think about it is like this. And so for external flow, we know that the flow turns turbulent when the Reynolds number is equal to 5 times 10 to the 5th. And so the expression for the Reynolds number is U infinity times the length divided by the viscosity. Okay? And so for these problems, the U infinity here is a constant. Right? And so that's given to the problem. That's the free stream velocity. The viscosity here is also constant because it's a physical property. Okay? Normally what you would do is you would plug in the entire length of the plate. And so I think that's what you did in the first part. But in this case, the Reynolds number is constant, so you solve for C. So yeah, I think you got it. Huh? You'll find that LC is very small. And that's on purpose. Thanks. Have a good day. Yeah. Any final questions from Zoom before I close up the call? Okay, all right. So see you guys Wednesday.